Welcome to G Fun Facts Online. Imagine everything you can see. The screen you're looking at, the planet you're on, the stars in the night sky. All of it makes up just 15% of the total matter in the universe. The other 85% is completely invisible. It's a mysterious substance scientists call dark matter. It doesn't emit, absorb, or reflect any light, which is why we can't see it. So how do we know it's there? We see its ghost. We see its gravitational pull on the things we can see, from the way stars orbit the centers of galaxies to the very structure of the cosmos itself. For decades, a global quest has been underway to unmask this invisible giant, using some of the most sophisticated and mind-boggling detectors ever built. Today, we're diving deep into the hunt for dark matter. The search for this elusive particle is a three-pronged attack, a coordinated assault on one of physics' greatest mysteries. The strategies are called direct detection, indirect detection, and collider searches. Each one offers a unique way to catch a glimpse of the unseen. First, let's talk about direct detection. This is the most straightforward yet perhaps the most difficult approach. The idea is to catch a dark matter particle right here on Earth. As our solar system barrels through the Milky Way's vast halo of dark matter, scientists predict that billions of these particles are streaming through your body every single second, but they almost never interact. So, how do you catch one? You build the quietest, most sensitive trap on the planet. Direct detection experiments are designed to spot the tiny recoil of a single atom's nucleus when it gets nudged by a passing dark matter particle. These experiments are feats of engineering, typically built deep underground in mines or tunnels. This massive layer of rock shields them from cosmic rays and other radiation that could create false signals. It's like trying to hear a pin drop in the middle of a rock concert. You have to go to the most soundproofed room in the world. The leading technology for this search uses liquefied noble gases, primarily xenon and argon. These detectors are called dual-phase time projection chambers, or TPCs. Imagine a giant, ultra-pure tank of liquid xenon. When a particle, hopefully a dark matter particle, strikes a xenon nucleus, it causes two things to happen. First, it creates an immediate, tiny flash of light, which scientists call the S1 signal. Second, it knocks a few electrons off the xenon atom. A strong electric field pulls these freed electrons up to the top of the tank, where they enter a pocket of xenon gas. As they pass into the gas, they create a second, much brighter flash of light, the S2 signal. Here's the brilliant part. The time between the first flash and the second flash tells scientists the vertical position of the collision. And by looking at the pattern of the second flash on a grid of sensors, they can pinpoint the horizontal position. This gives them a full 3D location of the event. But even more importantly, the ratio of the brightness of the two signals is different for a dark matter-like interaction versus a background particle. This allows them to filter out almost all the noise. Three massive experiments are leading this race to the bottom, pushing the limits of sensitivity. The first is Lux Zeppelin, or LZ, located nearly a mile underground in South Dakota. It uses 7 tons of liquid xenon and is currently the most sensitive dark matter detector in the world. Then there's XENONnT, its rival, located in Italy's Gran Sasso laboratory. It uses almost 6 tons of xenon and has incredibly low background noise, thanks to a system that continuously purifies the xenon by distilling out radioactive radon. The third major player is PANDAX4T, located in the China Jingping Underground Laboratory, the deepest lab on Earth. The incredible depth provides unmatched shielding from cosmic rays. So far, none of these incredible machines have found a definitive dark matter signal. But these null results are hugely important. They've ruled out a huge chunk of the territory where the leading dark matter candidate, a particle called the WIMP, was predicted to be hiding. Other direct detection methods include using supercooled crystals. The super CDMS experiment chills germanium crystals to just a fraction of a degree above absolute zero. At these temperatures, a particle collision creates a measurable vibration, or a tiny pulse of heat, alongside an electrical charge. By comparing the heat and charge, they can also distinguish dark matter from background noise. There are even bubble chambers, like the PICO experiment in Canada. They use a superheated fluid that's right on the edge of boiling. A dark matter particle could deposit just enough energy to create a single bubble, an event captured by cameras and even microphones that listen for the tiny pop of its formation. This technique is exceptionally good at ignoring most background radiation, which isn't strong enough to form a bubble. Now for the second strategy, indirect detection. If trying to catch a dark matter particle on Earth is too hard, why not look for the evidence of its destruction out in the cosmos? This is the goal of indirect detection. The theory goes that in places where dark matter is extremely dense, particles might collide and annihilate each other. This annihilation would produce a shower of familiar particles, like high-energy gamma rays, neutrinos, and antimatter. It's like looking for the smoke from a fire you can't see. Scientists point powerful telescopes at the most dark matter-dense places they can find. The prime target is the center of our own Milky Way galaxy. It's thought to have the highest concentration of dark matter nearby. The downside is that it's also a chaotic, busy place with lots of other things, like pulsars and black holes, that also produce gamma rays, creating a messy background. A cleaner target is dwarf spheroidal galaxies. These are tiny, faint satellite galaxies orbiting our Milky Way. They are completely dominated by dark matter and have very little gas or star formation, making them incredibly quiet. If we see a mysterious glow of gamma rays coming from a dwarf galaxy, it's a very tantalizing hint that it could be from dark matter annihilation. The Fermi Large Area Telescope, a space-based gamma-ray observatory, has been scanning the sky since 2008. It has set some of the tightest limits on dark matter by looking at these dwarf galaxies. Fermi also famously detected a mysterious excess of gamma rays from our own galactic center, which could potentially be a dark matter signal. But the jury is still out. On the ground, huge observatories like HESS, MAGIC, and Veritas use arrays of massive telescopes to detect something called Cherenkov light. When a high-energy gamma ray from space hits our atmosphere, it creates a cascade of particles that, for a split second, travel faster than the speed of light in air, producing a faint flash of blue light. These telescopes capture that flash, tracing it back to its cosmic source. Another messenger from dark matter annihilation could be the neutrino. These ghostly particles barely interact with anything, meaning they can escape from the dense cores of stars or galaxies and travel straight to us. The IceCube Neutrino Observatory at the South Pole is the world's largest neutrino detector. It uses a cubic kilometer of Antarctic ice, studded with thousands of optical sensors. When a neutrino happens to interact with an ice molecule, it produces charged particles that emit Cherenkov light, which the sensors pick up. IceCube has looked for neutrinos coming from the Sun, the Earth's core, and the galactic center, all places where dark matter could get trapped and annihilate. The third and final strategy in our three-pronged attack is collider searches. If you can't find dark matter in nature, why not try to make it yourself? This is the work of particle accelerators like the Large Hadron Collider, or LHC, at CERN. By smashing protons together at nearly the speed of light, the LHC recreates the extreme energy conditions of the early universe. The hope is that in the debris of these collisions, new, exotic particles, including dark matter, will be forged. But there's a problem. If dark matter particles are created, they're invisible to the detectors. So how do you see the invisible? You look for what's missing. Imagine smashing two billiard balls together head-on. The pieces fly out in all directions, but their total momentum pushing outwards should cancel out. Now, what if you saw all the pieces fly out to one side with nothing going the other way. You'd know an invisible piece must have been created and carried momentum away in the opposite direction. This is exactly what physicists at the LHC's giant detectors, ATLAS and CMS, look for. They analyze the collision debris and add up all the energy and momentum. If there's a significant imbalance, what they call missing transverse energy, it's a huge red flag that invisible particles, possibly dark matter, were produced and escaped undetected. So far, like the other searches, the LHC hasn't found definitive proof. But it has ruled out many theoretical models and provided crucial, complementary information to the direct and indirect searches. For a long time, the main suspect in the dark matter case was the WIMP, or weakly interacting massive particle. But as our biggest and best experiments keep coming up empty, scientists are turning their attention to other compelling candidates. The most popular alternative right now is a bizarre, hypothetical particle called the axion. Axions are predicted to be incredibly lightweight, and instead of behaving like individual particles, they would act more like a vast, classical wave washing over the galaxy. This requires a completely different detection strategy. The leading method is called a haloscope. The idea is that in the presence of an incredibly strong magnetic field, an axion can be coaxed into converting into a photon, a particle of light. A haloscope is essentially a highly sensitive radio receiver designed to listen for these photons. The Axion Dark Matter Experiment, or ADMX, is the flagship of this search. It uses a powerful superconducting magnet and a resonant microwave cavity, all cooled to near absolute zero to kill thermal noise. The experiment is like tuning a radio very, very slowly. If the radio's frequency matches the mass of the axion, the signal of axions converting into photons will be amplified, producing a tiny power spike, the telltale sign of dark matter. It's an incredibly delicate search for a single, faint station in a universe of static. The global hunt for dark matter is one of the most compelling frontiers of science. The challenge is immense. The signals are vanishingly small, and they are buried in a mountain of background noise from mundane sources. But the quest pushes us forward. A new generation of even bigger experiments is on the horizon. The LZ and XENONnT collaborations are joining forces to build a single, colossal xenon detector that will probe for WIMPs until they hit the ultimate background, neutrinos from the Sun. The next generation Cherenkov telescope array will scan the skies for annihilation signals with unprecedented sensitivity. And the search for axions is rapidly expanding, with new technologies designed to scan a wider range of possible frequencies. We still don't know what the dark 85% of our universe is made of. It could be WIMPs, it could be axions, or it could be something so strange we haven't even dreamed of it yet. But with thousands of scientists around the world building these extraordinary detectors, digging deep underground and staring into the heart of galaxies, we are getting closer to finally illuminating the unseen universe. Thanks for listening to Fun Facts Online.